The periodic fading of stars in the Crab Nebula is caused primarily by the presence of a neutron star at its center, known as the Crab pulsar. This pulsar is a strongly magnetized rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles. As the pulsar rotates, these rays spread through space like a lighthouse beam, creating the phenomenon of periodic dimming or pulsation when viewed from Earth. As it rotates, the pulsar produces intense bursts of radiation over a range of wavelengths, including radio, optical, and X-rays. When the beam of radiation is directed toward Earth, the star appears brighter. As the beam spins sideways, the star dims. This periodicity is incredibly precise. The Crab pulsar makes one revolution about every 33 milliseconds. The regularity of this pulsating effect is one of the most interesting characteristics of pulsars, providing important information about the rotation and magnetic field of the stellar remnant. The environment surrounding the pulsar is also significant. The Crab Nebula itself is the result of a supernova explosion that produced a pulsar in 905 AD. The expanding supernova debris interacts with the pulsar's magnetic field, creating a complex structure of shocks and radiation in different wavelength ranges. This interaction generates additional radiation that contributes to the observed brightness changes associated with periodic dimming. Studying the periodic dimming of the Crab Nebula, which is primarily due to pulsar activity, not only deepens our understanding of the life cycle of stars, but also provides insight into the physics of neutron stars and the extreme conditions that exist in their neighborhoods. Pulsars like the Crab Nebula provide a natural laboratory for studying fundamental questions in astrophysics, contributing to our understanding of the behavior of the universe and the life cycles of celestial bodies. The phenomenon of some stars appearing older than the universe itself is a fascinating mystery in astrophysics, arising from various factors related to the formation and measurement of stars. The age of the observable universe is estimated to be about 13.8 billion years old, based on cosmic microwave background radiation and other cosmological data. When astronomers observe certain stars that appear to be older than this time interval, this provides a deeper look at the intricacies of stellar evolution and the difficulties in age estimation. One of the main reasons for these apparent age discrepancies has to do with the methods used to determine the age of a star. Astronomers often estimate stellar age based on a star's position on the Hertzsprung-Russell diagram, where stars are arranged according to their brightness and temperature. However, this method can lead to uncertainties, especially for stars in later stages of evolution. If the star is in a part of the diagram that suggests a much older age, this may not accurately reflect its true age if the underlying assumptions about evolutionary processes are flawed or incomplete. Another factor contributing to this paradox is the nature of the star's composition. Stars with high concentrations of heavy elements, known in astronomy as metals, usually form after previous generations of stars have evolved and died, enriching the interstellar medium. Therefore, a star with low metallicity may indicate that it was born from primordial materials, suggesting that it has existed since the early universe. Nevertheless, stars with lower metallicity may appear older than they actually are because of the complexities of stellar dynamics and life cycles. In addition, some stars are part of globular clusters, which are dense clusters of ancient stars. The age of these clusters is difficult to determine precisely. The oldest globular clusters are estimated to be nearly 14 billion years old based on stellar models, making them seemingly bumping up against the upper limit of the age of the universe. Such a coincidence calls into question the very models we use to estimate stellar ages and star formation histories in the cosmos. In conclusion, the apparent older age of some stars challenges our understanding of stellar evolution and highlights the need for improved modeling techniques. As researchers continue to study these celestial objects with modern telescopes and improved techniques, we can further understand the tangled history of our universe and the stars that inhabit it. Ultraluminous X-ray sources, commonly referred to as ULXs, are unusual astrophysical phenomena found in various galaxies beyond our planet. They are characterized by incredibly high X-ray luminosity, 1,000,000 times the luminosity of the Sun. ULXs are of great interest to astronomers because they are some of the most intense X-rays observed in the universe and produce emission that often exceeds that generated by typical stellar sources. The exact nature of ULXs remains the subject of active research, but they are generally thought to be associated with binary systems involving a compact object, such as a black hole or neutron star, that accretes matter from a companion star. In particular, many ULX are thought to host black holes with masses ranging from a few to a few tens of solar masses, distinguishing them from the stellar mass black holes commonly found in our galaxy. The accretion process occurs when the matter of a companion star flows into a black hole, generating enormous amounts of energy as the falling material heats up and emits X-rays. Another intriguing possibility is that some ULX may be associated with intermediate mass black holes, which are a missing class of black holes that have masses between 100 and 1,000 solar masses. The detection of intermediate mass black holes in ULXs can shed light on the formation of supermassive black holes at the centers of galaxies, which can have masses millions or even billions of times that of the Sun. In addition, ULX can exhibit brightness variability, indicating a change in accretion rate. Sudden outbursts and fluctuations can provide additional insight into the dynamics between the accreting matter and the compact object. This variability often makes ULX a rich field for studying the fundamental physics of black holes, accretion flows, and the environments in which they exist. The study of superluminous X-ray sources continues to advance with advances in observational technology and observing campaigns in both the optical and X-ray wavelength ranges. As we learn more about these mysterious objects, they open a unique window into the extreme astrophysical processes and interactions between stars and their compact remnants, enriching our understanding of the cosmic landscape. Each discovery adds another layer to the tangled tapestry of the universe and spurs the quest to comprehend the fundamental nature of matter and energy in extreme conditions. The phenomenon of some galaxies having almost no star formation despite an abundance of gas is a fascinating area of research in astrophysics. At first glance, this seems counterintuitive. The presence of large amounts of gas, which is the primary fuel for star formation, should lead to active star birth. However, various factors can inhibit this process, leading to a condition known as star formation fading. One important reason for this attenuation has to do with the dynamics within the galaxy itself. In some cases, the gas in such galaxies may not be dense or cold enough to collapse into stars. Factors such as turbulence or heating from existing stars can prevent the gas from cooling and condensing, creating a barrier to star formation. For example, in some massive elliptical galaxies, the presence of supermassive black holes at their centers can drive powerful winds or jets that heat the interstellar medium, effectively slowing or stopping the cooling processes necessary for star formation. Moreover, galaxy mergers and interactions can greatly affect the rate of star formation. When galaxies collide, they can direct gas toward their centers, causing bursts of activity. But in other cases, these interactions can cause the gas to be expelled from the galaxy or redistributed in a way that prevents star formation. Gravitational forces can carry the gas away or create conditions that stabilize the gas against collapse into stars. Another factor may be the role of dark matter and the overall gravitational potential of the galaxy. For galaxies in which there is no active star formation, the binding energy of the dark matter halo may not provide the conditions necessary to effectively trap gas. Reduced gas volume resulting from interactions with the environment or from the higher gravitational potential in a galaxy cluster can also remove gas that would otherwise be available for star formation. In addition, the role of the cosmic web cannot be ignored. The large-scale structure of the universe affects the flow and distribution of gas. In some regions, the influx of gas from the intergalactic medium may be suppressed due to the large-scale environment, further limiting the amount of gas available for star formation. Understanding why some galaxies can retain significant amounts of gas without turning it into stars provides critical insights into the evolution of galaxies. By delving deeper into this topic using advanced observational and modeling techniques, researchers aim to unravel the complex interplay of gravitational, hydrodynamic, and chemical processes that have shaped the life of galaxies throughout cosmic history. Each new finding deepens our understanding of galaxy formation and evolution, revealing the complex nature of the universe in which we live. The ripples observed in the Milky Way disk are a remarkable phenomenon that allows us to understand the dynamics of our galaxy. These pulsations are primarily caused by the gravitational interaction of stars within the disk, as well as the influence of nearby structures. One important contributing factor is the passage of spiral arms. As stars and gas clouds move through these arms, they experience a gravitational pull that creates perturbations that result in wave-like shapes in the distribution of stars and gas. In addition, interactions with companion galaxies play a crucial role in creating these ripples. The Milky Way is not an isolated entity. Several small galaxies, such as the Large and Small Magellanic Clouds, orbit nearby. The gravitational attraction of neighboring galaxies can cause tidal forces that affect the distribution of stars in the Milky Way disk. Over astronomical time, these interactions can accumulate and create the observed waves or ripples in the galaxy structure. Another interesting aspect is the potential involvement of dark matter. Although we cannot see dark matter, it is believed to make up a significant portion of the galaxy's mass. Its gravitational influence may also contribute to the movement of stars, resulting in these rippling patterns. This concept allows scientists to study the influence of dark matter indirectly, through the behavior of visible stars. Researchers continue to analyze data from telescopes and other instruments and reveal the complexity of the Milky Way's structure. Understanding these ripples not only helps us understand our own galaxy, but also sheds light on the interactions occurring in other galaxies throughout the universe. Each ripple tells a story of cosmic motion and the gravitational dance between celestial bodies. The intricate and symmetrical shapes of some planetary nebulae result from a complex interplay of processes late in a star's life. When a medium-sized star like our Sun exhausts its nuclear fuel, it undergoes a series of transformations. When the core contracts and heats up, the outer layers of the star are ejected into space, forming a glowing shell of gas and dust known as the planetary nebula. The symmetry often observed in these nebulae can be explained by the dynamics of the ejection process. One of the main factors influencing the shape is the role of magnetic fields. When a star sheds its outer layers, magnetic fields can create organized structures within the ejected material. These fields help direct the flow of gas, resulting in more uniform, complex shapes rather than random distributions. In many cases, these magnetic fields also interact with the stellar wind, a stream of charged particles ejected from the star, reinforcing this ordered structure. In addition, binary star systems contribute significantly to the formation of symmetric shapes. If a star exists in a binary system, interactions between two stars can lead to mass exchange and the formation of ejected material. A single star can shed its outer layers while a companion gravity attracts and directs this material, creating a more structured and recognizable shape. This gravitational interaction can lead to the formation of jets and lobes that produce the unique and often beautiful shapes we observe. The combination of these processes creates the breathtaking patterns observed in planetary nebulae, which can range from circular and spherical to more complex shapes, including intricate knots and filaments. Studying these structures not only deepens our understanding of stellar evolution, but also provides clues about the physical conditions late in the life of a star. Each planetary nebula is a snapshot of cosmic processes, demonstrating nature's mastery of the universe. The interstellar object known as Oumuamua has intrigued scientists since its discovery in 2017, providing a unique opportunity to study a visitor from outside our solar system. Oumuamua is believed to have a rocky or metallic composition, and its unusual shape is elongated and cigar-shaped, which is very different from typical asteroids or comets found in our solar system. The name Oumuamua comes from the Hawaiian language and means scout or messenger, which is quite reflective of its status as the first detected interstellar object to pass through our planetary neighborhood. Scientists hypothesize that Oumuamua originated from a star system beyond our planet, as a result of an ejection from its home galaxy. This ejection could have been caused by gravitational interactions with other stars, which could have caused it to be flung away at high speed. Freed from its original star system, Oumuamua traveled the vastness of space for millions of years, eventually making its way to the inner solar system, where we discovered it. Another intriguing aspect of Oumuamua's journey is its trajectory. As it traveled through the solar system, the object exhibited unusual acceleration, which some scientists initially attributed to outgassing, a common phenomenon observed in comets. However, the lack of a visible comet-like tail led researchers to consider alternative explanations, including the possibility that it was a fragment of a larger body, or perhaps playing some role in the complex dance of interstellar dynamics. Ultimately, Oumuamua serves as both a scientific mystery and a reminder of the dynamic nature of the cosmos. Its presence raises fundamental questions about the distribution of interstellar objects and the processes that govern their movement through space. Through continued research and observations, scientists hope to learn more about the origin and properties of such guests, leading to a deeper understanding of the universe beyond our solar system. The presence in some star clusters of several populations of stars with different compositions provides a glimpse into the complex history of these celestial formations. In particular, the phenomenon is most prominent in globular clusters, ancient groups of stars orbiting galaxies. The different populations can be attributed to the environment in which the clusters formed and the subsequent evolutionary processes through which they passed. One of the main reasons for the multiplicity of populations is the initial conditions of cluster formation. Many star clusters formed in dense regions of gas and dust, where the first generation of stars created heavy elements through nuclear fusion. When these stars reach the end of their life cycle, they enrich the surrounding matter with heavier elements, a process called metallicity. The enriched gas subsequently became the raw material for the next generation of stars, giving rise to a second population with a different composition, often exhibiting higher metallicity than the first. In addition, the diversity of stellar populations can be facilitated by interactions between stars within a cluster. As stars evolve, some of them may eject material that can be accreted by younger stars, further changing their chemical composition. It is also hypothesized that in some clusters, periods of star formation extended over millions of years. These intervals allowed different compositions to form as the stellar environment evolved. Moreover, in some cases, the detection of multiple populations challenges previous ideas about how star clusters evolve. The idea that globular clusters may have formed from the merger of smaller clusters suggests that what we see today is a mixture of different star formations sharing space in the gravitational capture of the cluster. This complex interplay of formation history and stellar evolution makes the study of star clusters particularly fascinating because they reveal the processes that shape the universe on vast scales. Each cluster contains a wealth of information about the life cycle of stars and the chemical evolution of galaxies. The periodic brightening of the blazar OJ 287 is a surprising phenomenon that has attracted the attention of astronomers for several decades. Blazars are a class of active galactic nuclei characterized by powerful jets of relativistic particles pointed almost directly at Earth. These jets emit radiation throughout the electromagnetic spectrum, and OJ 287 is particularly notable for its brightness fluctuations, which occur about every 12 years. The periodic activity observed in OJ 287 is explained by the interaction of a supermassive black hole at the center of the galaxy with another black hole. This system consists of a primary black hole actively accreting matter, surrounded by a secondary black hole in a binary system. When a companion black hole orbits around a larger black hole, it exerts a gravitational influence on the material of the accretion disk surrounding the main black hole. This gravitational influence can enhance the accretion process, resulting in increased radiative power as the companion black hole approaches. During periods of increased activity, the energy released as matter spirals into the black hole increases significantly. This outburst leads to a sharp increase in the brightness of the blazer, causing the flares observed from Earth. The mechanism of these flares may also involve a complex interaction of shock waves propagating down the jet, further enhancing the brightness through the Doppler effect as the material travels at close to the speed of light. The cyclicity of OJ 287 strengthens the understanding of black hole interactions in active galactic nuclei. Observations of its amplification not only provide insight into the behavior of matter under extreme conditions, but also help improve our knowledge of the dynamics of such massive systems. OJ 287 serves as a critical source of information in the quest to comprehend the workings of the universe at its most energetic and fundamental levels. Binary systems often go through a stage known as common envelope evolution, which can significantly change their structure. This occurs when one of the stars in a binary expands into a giant star, enveloping the other star in a shared outer layer of gas. Gravitational interactions between two stars can cause an abrupt transformation of their orbits and potentially lead to the ejection of the outer shell. However, some binary systems manage to survive the common shell phase, and this resilience can be explained by several key factors. One important factor is the ratio between the masses of the two stars. If the secondary star is massive enough, it can help stabilize the common envelope phase by retaining some of the material ejected from the primary star. Eventually, this containment may allow the two stars to continue interacting, facilitating additional mass transfer and allowing them to remain bound together. The interaction with the secondary star also helps dissipate energy, which can prevent the envelope from dissipating too much, allowing the binary system to evolve successfully. In addition, the dynamics of the common envelope itself plays a significant role in the outcome. During this phase, stars can undergo dramatic changes, including a rapid decrease in orbital distance. If the energy released when the primary star's envelope collapses into the companion core is enough to completely expel the common envelope, the evolutionary path may lead to a closer binary configuration. A closer orbit could bring the two stars closer together, increasing the rate at which they interact and setting the stage for future evolution. The presence of additional factors, such as the spin and rotation of the stars, can also affect the ability of a binary system to undergo common envelope evolution. The orientation of the star's spins and their magnetic fields can affect the physics of the shell dynamics, thereby influencing whether or not the binary system can survive. In cases where the stars are favorably located, this interaction can help the system maintain its integrity and prevent it from completely collapsing. These mechanisms demonstrate that binary systems are capable of a variety of evolutionary pathways that allow them to adapt and survive even after intense transformations. Understanding how these systems cope with such transitions provides insight into the complex life cycles of stars and the intricate relationships that can form in the cosmos. Each binary system offers a unique story about stellar evolution and the diverse outcomes that can result from the interaction of massive objects in space.